We all know this forward bias and reverse bias. So let's look at the current flow part here. You all know this. All right. So the first issue is a qualitative understanding of why does a PN junction rectify. Large current in one direction and significant current in one direction and small current in the other direction. That's what we mean by rectification, right? There's a difference between asymmetry between forward and reverse bias. Why? All of you have done PN junction. So what is the explanation? How do you explain this? Why does it allow a lot of current in the significant current in the forward and very little current in the reverse? What is happening? Right, you go for a job interview. Why does a PN junction rectify? You have 5 minutes to answer. Right, explain. Huh? Charge carriers are injected from both sides. Okay, why are they not in depletion width is increasing in forward bias, decreasing, okay, and increasing in reverse bias. Okay, so what does depletion region have to do with current? Huh? Barrier height. All right, can we write down a few sentences, let's say, if you have to explain? Okay, let's see. What is the first sentence I should write down? Say you're allowed 3-4 sentences to explain. What is the first sentence I should say? Why does a PN junction rectify? What will you write? Okay, so is everybody agreeing? Okay, so you're saying depletion width, so you're focusing on increases under reverse bias, and decreases under forward bias. Okay, fine. All of you can explain this, right? All of you can explain this? Why it increases in reverse? We just saw in forward bias the net voltage across the junction becomes VBI minus V, and in the reverse bias the net voltage will become VBI plus VR. Okay, so fine. What is the next sentence you want to say? Huh? Depletion width increases under reverse bias and decreases under forward bias. Okay, so that's a fact, we agree. Okay, next. Huh? Barrier height. Everybody is agreeing on barrier height? What do you want to say about barrier height? Barrier height decreases under forward bias and increases under reverse bias. Okay, fine. Then 3. Huh? No, so you have to state fact number 1, fact number 2, and then it's like a theorem, right? You write this and then you say, hence proved that PN junction should rectify. So you state your case like that. Hence proved. That's what I'm looking for. No, charge flows. From where are you saying this? Oh, so from here you're saying, from 2, you're saying charge can flow across the junction in forward bias and not in reverse bias, right? Is that what you want to say? because of the barrier? Hence proved, is it? Can I now write hence proved? You want to say that? Or you want to write one more statement or something else you want to write? One more? Which one? Huh? Yeah, that's fine, na? A barrier height decreases under forward bias and increases under reverse bias. Okay, so you are saying 4. So number 4 is saying when V becomes larger than VBI, significant current flows. All right. So you are saying I've removed the barrier? Huh? No, wait. You're saying I've removed the barrier. Because we just saw that the barrier becomes VBI minus V. Right? By drawing the band diagram. If you make V larger than VBI, you're saying I've eliminated the barrier. Huh? So now, you tell me, is 1 really necessary? Why can't I simply say barrier height decreases under forward bias, increases under reverse bias? Why do I need to invoke depletion region? When you apply in forward bias, the net voltage is VBI. When you apply forward bias, it becomes VBI minus V. When you apply reverse bias, it becomes VBI plus V. So why do you need to say this? Can't I cross it out? You don't need this. Why were you all starting with depletion with? This is okay. I can justify it straight away. In forward bias, VBI minus V. Reverse bias, VBI plus V. That's the barrier height. So I don't need this. So if you guys are starting with depletion width, you are unnecessarily starting with it. In fact, it's the other way around. If you're thinking depletion width increases and that causes the barrier to increase, it's the other way around. The barrier, the net voltage becomes smaller, and that causes the depletion width to become smaller. The net voltage across the junction becomes VBI plus V, and that causes the depletion. Is this way the argument is flowing and not this way? It's not flowing that way. Okay? So this is wrong. Right? So you lose 1/3 marks. You've given 3 you've given 3 points, 1/3 gone. Okay. The second one I grant you. Okay? Second one is fine. Charge can flow across the junction in forward bias and not in reverse bias. Huh? This is sort of problematic. This is problematic. We'll just see in a minute, it's problematic. This is totally wrong. This is totally wrong. V is significant current flows when V greater than VBI. Not true. Not true at all. Okay? So if you're just leaving at this, okay, we agree with this, and if you're leaving at this, charge can flow across the junction in forward bias and not in reverse bias, may be true, but if you're saying that it follows from here, then you're not right. You're not right in this. That just because the barrier increases and therefore, and you're not, this is where you need to understand, and this is totally wrong. So you can see here, all of you have done PN junction in some form, but in fact, there are so many misconceptions regarding PN junction. So many misconceptions. In books also, we just saw about depletion approximation. Even for why the students carry a lot of misconception regarding why a PN junction rectifies. Okay, so let's okay, before we continue, we need if we need to have discussions like this, then obviously, you can see where we are. My target was to cover MOS and all those things, and we are still at the PN junction. I need at least one extra class. One extra class, which is tomorrow, Thursday. Quiz is on the last day of the class, we just said. Quiz is on 15th in the class. So we are losing a lecture there. And I need a lecture tomorrow, 7th. So what would be a convenient time? Any time of the day is fine. 5 to 6? No? You have a class? 4 to 5? 4 to 5? And anybody here has a problem with 4 to 5? Because I want to spend a little bit time solving depletion, solving Poisson's equation under different cases is important. So I want to do mostly a problem solving. And how do we solve Poisson's equation? Because you need to do that for metal semiconductor junction, you need to do for PN junction, for MOSFETs, everywhere. So how do you go about, in a simplified manner, how do you go about doing it? So let's keep tomorrow 4 to 5. Can we start a little early also? 3:30? Huh? 3:30? Okay, so let's start. I'll find a room and we'll convey it to you, right? 3:30 till you get tired or till you have a class, okay? All right. Okay, so what is the problem with our explanation? So you guys are saying the following. Let's see. You are saying, here is my PN junction. Right? You are saying PN junction, okay? And you are saying the following. That there is a barrier, correct? The barrier is in which direction? If I'm looking at it, which side is at a higher potential? N side is at a higher potential, right? So it's as if this side there is a barrier, N side. So if I were to draw in terms of potential, so the potential is like this, right? Potential psi goes like this here, and there's a barrier, VBI. Correct? There's a barrier. So if I have holes here, right? Let's look at forward bias. So forward bias is you're going to apply positive here and negative here. In which direction do you want current to flow? Positive here, so the direction of current flow is like this here, right? This is the direction of current flow. Okay, in which direction are you asking holes to flow? If current is in this direction, J, in which direction are you asking holes to flow? So you're asking holes to flow like this, right? Hole flow. In which direction are you asking electrons to flow? Huh? Because note the direction of the current, J, so you're asking electrons to flow like this, right? Okay. Why are the holes finding it difficult to go from left to right? Why are the holes finding it difficult to go from left to right? Because there's a barrier, right? There's a barrier, VBI. Same way, the electrons also see a barrier. The electrons also see a barrier of VBI. So both electrons and holes see a barrier. And so you are saying, by applying a voltage V, I lower the barrier to VBI minus V. And thereby, this is what is preventing, right? I have a lot of holes here. See, a lot of holes here, and very few here. So holes have a natural tendency to go towards the N side via which process? Diffusion. They would like to diffuse. But what is preventing it from going towards the N side? This barrier. Either you look at it in terms of electric field or you say a barrier. So the barrier is preventing the holes from going. So the moment you lower the barrier, well, the holes start going to the other side. And same way happens to the electrons. And note that we know that whenever something is barrier related, it always flow is related to e to the power minus phi by kt. It always goes like this. Anything which is barrier related, the probability of crossing the barrier goes as exponentially with phi here. Okay? So current starts increasing exponentially. The moment you lower the barrier, because at equilibrium you have zero current, the moment you lower the barrier, the holes spill over. So the current starts increasing exponentially. No problem. So that on that count you are right, that when I apply a forward bias, I lower the barrier, holes can now go over to the n side. Electrons from n side can come to the p side. Current starts to flow. And current starts to flow, I versus V, well, it starts to flow here. Now this is where there is a error here, because your IV characteristics under linear, in a linear plot, see, this is a linear plot, conveys an impression, a wrong impression that current only starts here. This is another major mistake that happens here. People think current starts at that particular point, you know, when you plot it. But that's a totally wrong thing that you get. If you simply plot L and I versus V, you see it's a straight line. Current is flowing all the time. Current is flowing all the time. I'll direct you to more on this so that you can see later on. Current starts immediately as you make V positive, current starts. Current is small, but current keeps on increasing. There is no, that's what I said, there is no cut in voltage. This is another cut in voltage that you've heard. Cut in voltage, the concept of cut in voltage is wrong. All the books talk about it, everywhere you've heard about it, it's a wrong concept. There is no cut in voltage. There is no unique point at which the current starts to flow. Current is flowing here. Current is starting to flow here, everywhere it is flowing. There is no unique point. The unique point only comes because you plot things on linear scale. Any sharply varying curve, any curve which is highly nonlinear, if you plot it on a linear plot, it would appear as if it doesn't have to be exponential. Anything, it would appear as if it's increasing sharply at some point, and will give you an impression as if there's something very interesting, magical happening at that point. In fact, nothing is happening. It's just a nonlinear curve on a linear plot. If you show it, it appears as if there is something here. There is no cut in voltage. And you can see it if you plot it on a log scale. There is no unique point in a PN junction at which significant current starts to flow, because significant depends on you. Who defines significant? I mean, what do you mean by significant? There's no such thing as this one here. There is no cut in voltage, by the way. Current starts to flow throughout, forward bias. At every bias, current is flowing. At every bias, current is flowing, and you know, in forward bias, it goes as e to the power qv by kt. All of you know that. It doesn't say this equation that you know, we will derive it, I equal to is e to the power qv by kt. Have you ever heard that this equation is only valid for V greater than V gamma? No. There's nothing like this. This equation is all the time valid in forward bias. It's not about, there's no V gamma. Okay, so there is no cut in voltage. So you're right. When you apply forward bias, you're lowering the barrier. You're allowing holes to go to the other side by a natural process. Diffusion drives them, and electrons come to the p side. Diffusion drives them, and current begins to flow. And current keeps on increasing exponentially. Let's come to the other part. This is where there's a little bit of a problem. This is where reverse bias. Let's look at a reverse bias situation. Pn, let's apply okay, there's still a barrier. The barrier becomes now, if you apply a voltage VR, the barrier becomes VBI plus VR. Right? The barrier, all of you know, whatever reverse bias you apply, the barrier becomes larger. Okay, in which direction do you want current to flow? What is the direction of current flow? Direction of current flow is right, because you've applied a positive bias. That's how the current would flow. In which direction are you asking holes to flow? In which direction are you asking holes to flow? If the current is there, hole flow, right? This is J, this is hole flow. In which direction are you asking electrons to flow? Okay, correct? Now, let me draw the barrier again. The barrier is VBI plus VR. This is the P side and this is the N side. In which direction are you asking holes to flow again? You're asking holes to flow from where? N to P. So we are talking about holes flowing from N to P, right? Do the holes see a barrier? Yes? Do they see a barrier? The holes have to go here. Where do they have to come? This is potential, by the way. I'm plotting psi. Do the holes see a barrier? Barrier plays no role. In fact, the holes would nicely like to go down the voltage. So if you're saying I've increased the barrier and that's the reason why current is low, that's not true. Holes don't see a barrier. Holes don't see a barrier. Where are you asking electrons to flow? Electrons, you are asking, if you draw the band diagram, you're asking electrons to flow in this direction. The electrons also don't see a barrier. They don't see a barrier at all. I mean, there is a potential barrier, but note that for the electron, if I have an electron here, electron would nicely like to go, because if you draw the band diagram will look like this. The electron will nicely like to go. It has no problem in going to the other side. It's falling down. And the electric field is such, electric field is in this direction. So why is the current in reverse bias small? So please put, that's where I said it's not entirely right, your explanation, because in reverse bias, you are asking holes to flow from N to P. You're asking holes to flow from N to P, and N region has very few holes. And you are asking electrons to flow from P to N, and P region has very few electrons. It's not that the electrons find it difficult to go. That's not the problem. The electrons can, electron from a hole from here very easily can come here. No issues. The problem is I don't have enough holes. Supply of holes is so little here. That's the reason why very little current flows in the reverse bias direction. Not because charge cannot flow. I mean, charge cannot flow, but why it cannot flow? Because there are very few charges there. And this you have to understand very carefully, that there are very few charges on the N side, very few holes on the N side, and very few electrons on the P side. That's why the current is very low. If by some means you can increase what are you asking for? You're asking for holes here, right? Holes here. And you're asking for electrons here. If by some means you can increase the number of holes in N side, what would happen? There is still a large barrier, but current will increase significantly. For example, if you were to shine light, what would happen? Light would create electron hole pairs. Suddenly you have increased the number of holes in this region here. And the holes fill nicely. Current increases significantly. So it's not about barrier. That's what I wanted to say. It's not about the barrier and reverse bias. Barrier causes no problems for you. The problem is supply of holes here and supply of electrons on the P side. That is the problem. That is what is causing very little current in this thing here, in a PN junction. So forward bias, you're right. Forward bias, you're reducing the barrier. Holes see a smaller barrier, they're able to cross. Electrons see a smaller barrier, they're able to cross. That's fine. In reverse bias, the problem is not the barrier, but reverse bias, the problem is availability of carriers. The carriers are very few. Barrier can be large, small, whatever, but if by some means, and this takes you to a very interesting case of the bipolar transistor. Right? So bipolar transistor, if I were to write here, all of you know this, we won't have time to look at bipolar transistor, so at this stage you can see here. So I have here, say, let's talk about P here and talk about N and P here, right? And you guys know that very well that you forward bias this junction, right? You forward bias this. And you know very well that you, under normal cases, you reverse bias this, right? This is a reverse bias junction. Reverse bias here. and forward bias here. But it's a reverse bias junction. There is a barrier. You know, you can apply 5 volt here. And if the VBI is 0.8, then the total barrier becomes 5.8. Because it has total barrier is 5.8, right? But then you forward bias it here. You apply 0.65 here. And suddenly what have you done? Why is this current in this junction very small? Because there are, remember, you are asking holes to flow in this direction. There are very few holes in the N side. Right? That's why current is very small in the reverse bias junction. But suddenly you forward bias this particular junction, and what does this junction do? It pushes holes on the N side. Suddenly you've increased the number of holes on the N side. And now these holes can very nicely flow to the P side. So a lot of current flows across a reverse bias junction. Bipolar transistor you've seen, all of you have seen. Collector based junction is reverse bias. A huge amount of current flows. And it's got nothing to do with barrier. I have a large reverse bias barrier. It has all to do with how many holes are there in the N side. That is the key parameter under reverse bias case. And by forward biasing the PN junction, what you have done is you've increased the availability of holes on the N side, and thereby a lot of current flows. A reverse bias junction carries a lot of current. Okay? And you start getting a current flow from emitter to base to collector and all of that is there here. Okay? All right, so with that, now you need to revise it. So your statement number 1 is not necessary. Statement number 1 is not necessary. Statement number 2 is fine. Statement number 3 is fine for forward bias. For reverse bias, you need to explain why small current flows under reverse bias, because of availability of carriers. And statement number 4 is wrong. Current, as I said, starts to flow immediately as you forward bias the junction. There is no unique point at which there is no cut-in voltage. And in fact, what happens is, so what happens is the current in a PN junction that flows here, when you increase it, what happens is initially the entire voltage that you apply gets dropped here. But as you keep on increasing the bias, note that these are also resistive regions here. So voltage increasingly starts dropping across these resistive regions here. So in fact, under most conditions, you are always, V is always less than or equal to VBI under forward bias. The VBI minus V is always greater than 0. There's always a barrier. You don't end up eliminating the barrier. Right, so that situation, before you start getting into when V becomes very close to VBI, you start getting something like this, and current starts saturating. Current starts saturating; it doesn't increase, and there are drops which start occurring somewhere else. Okay, so if time permits, we can see that later on. So V is the voltage across. You're not eliminating the barrier. Okay, all right. So with that in mind. So we know how the current flows here. So one of the key things is, if you want to look at forward bias, so we know that under forward bias, what is happening is holes are going over to the N side and electrons are coming over to the P side. And so what you end up getting is you start getting excess carriers. Excess carriers are on the N side, excess carriers are on the P side. In fact, if I were to plot, this is excess carriers here, delta. Delta Px will go like this because holes have been injected to the N side. So you have excess holes here. And the excess holes are, we've already seen that the holes will diffuse, will recombine, and that's the reason why they're falling here. And on the other side, you have excess electrons, delta Nx. The excess electrons also go in a similar manner here. All right, so how do we compute current? Okay. All right, so let's start with the current flow. How do we compute current flow? So the equations for U are the standard equations by which you know. continuity equations, Poisson's equation, current equation, all the equations you know, all right? So let me start with continuity equation. These equations you know are there. And we are talking about steady state. So del P by del T is 0. 0 here, 0 here. Okay. And generation rate, you know, Gn equal to Gp. If you're creating an electron, you're also creating a hole. If you're recombining an electron, you're also recombining a hole. So Rn equal to Rp. And I can combine these two equations. This is a very general. I may not have generation. I may have generation, you know. So a very general equation. I can combine them and write 1 over Q del Gn plus Jp by del x equal to 0. What this tells us is J total, which is Gn plus Js, is constant. The total current flowing through the device under steady state is a constant, right? Jn plus Jp is constant. So now the interesting thing comes. Gn plus Jp is a constant. So it tells us that if you compute the current at any point, I have a PN junction, right? PN junction. If you compute the current at any point, the point could be here, the point could be here, the point could be here, any point, A, B, C, anywhere. If you could compute, you've computed the current everywhere in the PN junction. Why? Because Jn plus Jp is constant. So the key issue then in PN junction becomes, what is, at which x do I compute? Where do I compute the current? So you would obviously, if current is the same everywhere, I can compute it at XA, at XB, at XC, compute it anywhere. So, and the current would come out to be the same. So now the issue becomes is, choose a x at which the computation is, as a person doing an analysis, you would choose a x where the computation is easy. Although all places will give you the same current, some places current is really hard to calculate. And some places the current is easy to calculate. All places are not the same. Although the same current flows everywhere, calculation of current at each place is, at some places easy, some places difficult. This is a very important point because it shows the first person who did the calculation was Shockley, the inventor of the transistor. He's the one who described the current flow in a PN junction. He derived an expression for current in a, and it's a beautiful derivation. It's appreciating. It's a very nice derivation that he has done for PN junction. And why is it very, very nice is because, as I said, it's not obvious. Where do you compute? A, B, and C. Let me tell you why it's not obvious before we start looking at. Okay, why it is not obvious. Let's look at. Right, this is PN junction. So we are talking about, let's say, forward bias, but reverse bias is also similar. Right? The result that you need to keep in mind is J equal to Jp plus Jn. And the other thing that you need to keep in mind is Jp is Jp. Okay, so let's write it down. Qp mu p E minus Q dp del p by del x. And similarly, Jn is Qn mu n E plus Q dn del n by del x. Right? Now, so to calculate currents, I have to calculate what? Two, Jp and Jn. To calculate Jp, I need to calculate this and this. To calculate this and this. In general, I require how many? I need to calculate four current components. 4 current components. Now, as a strategy, where would you calculate current? You know the answer. I know some of you know the answer, but don't go by that. From your past experience. In general, you would think, let me calculate the current, because if I have to calculate 4, you would think that maybe my calculation will become very simple if I have to compute only one component. Is that really possible? Think about it. So what is happening is, keep in mind that these lengths are very, very large. Right? So we are taking this L as very large. Very large meaning what? Much, much larger than diffusion length, hole diffusion length. So if you think about what is happening, you have forward bias. So let's look at, for example, current here. So you have injected holes. But what would happen to these holes? They recombine. So if I go far away, if I go somewhere here, what will happen to number of holes? All the holes have recombined. So there are hardly any holes left. All the holes have recombined, there are hardly any holes left. Right? What is the background amount of holes in N region? Very small. And the holes that you injected, they've all recombined. So if I look at a region such as 1, I will find, well, I don't have to compute P at all. No computation of P required. Because all the holes have recombined, there are very few holes. I don't have to compute P at all. Well, then if I go here, N, well, if I look at this particular region, it's a uniformly doped PN junction. This is also gone. I don't even need this. So I need to only compute Q, N, mu, and E. Not only that, I'm in a very good position. I know N equal to ND. That's the doping. So J equal to Q, ND, mu, and E. Right? I have to compute only one component. And not only that, only one variable. Only one variable. All I need is electric field in there. That's it. There are no holes, uniformly doped, N equal to ND. I need to just compute electric field. And you can break your head, you will never be able to compute the electric field. You'll never be able to compute the electric field at this particular point. Why? Why will you not be able to compute the electric field? Because note that in equilibrium, what happens to electric field in this region? 0. So E is to begin with 0. Now you apply a voltage, right? You apply a voltage. Where does all the voltage go? They all go here. And very little remains here. And it's very hard to calculate how much remains here. In fact, I can say this voltage that you applied, I can say the voltage across the junction becomes VBI minus V. That's reasonably. But I can't say what is the voltage in this region. You can't calculate. It seems it's so simple. I'm only one variable, but that one variable I cannot compute. I can simply not compute. And so your strategy fails. Your strategy will fail, you will not be able to calculate, and therefore this method gives us a big cross here. Doesn't work. Why I'm saying it is, tomorrow, if you're a device engineer, you're trying to analyze something, and some things may seem easier, but you'll falter. Okay? All right, so this doesn't work. The next thing that you will say is, okay, let's come back to PN junction. So you're saying that whatever voltage you apply, it goes across the junction here, right? It goes across the junction. So why not compute the current, let's say at this point? At this point, right at that particular point. Compute the current here, which is the x equal to 0 here. And for the sake of discussion, because I know now this entire voltage is dropped here, so we've already done the depletion approximation, we can calculate electric field and all of that is there here. So why not do the calculation at this particular point, at the center? And let's say we take a simple case, we take ND, we take a simple case where we talk about ND equal to NA. Let me just make the case even simpler for you. ND equal to NA, and artificially, let's make mu n equal to mu p. Just for the sake of discussion right now. Mu n equal to mu p, ND equal to NA. Right? Again come back, J equal to JP plus JN. So JP is QP mu PE minus QdP del P by del X. Right? And because of the way I've done it is that if I compute JP, I know JN right now because ND equal to NA, mu P equal to mu N. So, and everything else is the same. Tau P equal to tau N, all whatever is true for electrons, true for holes. Just to simplify and see, okay? So if I compute JP, I know JN. So I need to only compute JP. JN is already known. Now to compute JP, I need to compute this and this. These two quantities. Now I'm not going to go into the details here, but let me tell you, first of all, note that V equal to 0. Equilibrium. Do you and focus on point X equal to 0. Do you think there is this component is there? QP mu PE is there or not? There are holes in the depletion region. We just saw in the last lecture. There's an electric field. This is there. And you would agree, this is also there because the net current is 0. A drift current is there and diffusion current is there. Both are there. How much do you think they are there? How much do you think they are there? Well, you guys can calculate. Why? Because let's say, that's why I'm taking at the center. Center, right? So at the center, let's calculate the first component. Can we estimate the first component, the drift part, Q? What is the hole density at the center, Ni, in equilibrium? Mu P. And what is the electric field across the junction? Well, electric field across the junction, we already know the expression that is there for you, right? Electric field is expression there, which is the E max, maximum electric field. So all of these things you can calculate at equilibrium. Please go ahead at, when you go back, go ahead and calculate this value. I don't know the value right now, but this value will turn out to be, this is my, depends on numbers of course, may turn out to be something like 10 to the power 4 ampere per centimeter square. Okay? Just as an example, it could be 10 to the power 3 also. So if this is 10 to the power 4, this thing would also be 10 to the power 4. I don't need to calculate. 10 to the power 4, 10 to the power 4. Drift and diffusion are cancelling each other. Okay? So this is the situation at equilibrium. Note that equilibrium, J equal to 10 to the power 4 minus 10 to the power 4 equal to 0. Now you apply a forward bias. Right? Forward bias. How does the current flow in forward bias? There is an imbalance between the two. What will happen to, let's say this is diffusion and this is drift. What will happen to diffusion? Will become a little larger. So now think about that this is something X, this is something Y, right? I don't know what is the diffusion current, I know what is the drift current, but I know what is the net current here. Suppose I know the net current, and the net current is 1 ampere per centimeter square. Suppose by some means I measure or whatever I calculate 1 ampere per centimeter square. Now what do you think has happened? At equilibrium, diffusion was 10 to the power 4, drift was 10 to the power 4, they were cancelling perfectly. Now you applied a bias of 0.65 and you have a current of 1 ampere per centimeter square. What do you think has happened? X has become slightly larger than Y, but how much larger than Y? How much larger than Y? Because the current is 1 ampere per centimeter square. So how much larger? Huh? So if this is 10 to the power, if this is 1 times 10 to the power 4, so the current, and let's say for a moment Y remains unchanged, for a moment. So then X has become 1 point, how many zeros? 1, right? Into 10 to the power 4. And Y, let's say, is 10 to the power 4, right? So if you have to calculate current at the junction, what do you have to do? Calculate X, correct? And X to how much accuracy? 1, 2, 3rd to the 4th decimal place. You have to calculate X to the, you have to estimate diffusion current to the 4th decimal place. I mean, in any analytical calculation you show me, you can calculate something to the 4th decimal place, or 3rd decimal place, or the 2nd decimal place. We're talking about 10% error or 1% error. There's no way you can calculate that accurately, because you have two current components and they're balancing each other. One component becomes slightly larger than the other. Fine, and causes current to flow. But I can't calculate. How do I calculate X which is to that accuracy? I can't do that. And therefore, this is also out. I can't calculate current at the center. So I can't calculate here, I can't calculate here, I can't calculate here. Now, if you're Shockley, you're saying, where do I calculate? Right, where do I calculate? How do I calculate the current? Where do I calculate? And then you'll see he goes and calculates here. But then, here also he ends up with trouble. He ends up with trouble here also. At the edge of the depletion region, also he ends up with trouble. Okay? And so then he ends up with trouble here. So what he says is, I'm going to calculate partially here and sum up and then calculate. So if you look at somebody who's doing PN junction derivation for the first time, if you just try to recreate the atmosphere, you'll say, well, I tried here, I tried at the center, I tried here, I tried, nothing is working out. And then, you know, you have an insight, and then you see, well, those are maybe the right places to calculate. You can try here. Every place you will fail. Every place you will fail to calculate the current, except for two unique points. That's it. That's where you need to calculate, and you will get the answer. Okay, so what we were looking at is current flow in a PN junction, and so we have a voltage applied here, and we had one result from continuity equation. From continuity equation, if you recall, we had obtained this particular result, that Jn plus Jp equal to J, the net current is constant. Is constant. So we can evaluate current anywhere in the PN junction, and that current would be the same everywhere. So the issue was where do we determine J? If it's the same everywhere, where do we determine it? At which point do we sum up Jn and Jp to obtain the J here? And we saw that a location such as here, say location A, we saw current J is only equal to Jn is only equal to Qn mu n electric field, and we know n equal to Nd, but it's very hard to determine electric field there. The region is practically neutral, and whatever voltage we have applied, that particular voltage goes and drops across this particular region here. So it's very hard to determine. To determine field, we have to know how much is the voltage drop in that region. It's very hard to determine what is the voltage drop around A, because most of the voltage that we have, it goes here in this particular region, depletion region. Very, very small, we'll see, appears across the neutral region. And so that's very hard, even though we have one single component, but the determination of current determination of field at that particular point is difficult. The other one was, well, what about a point B, a location B? And location B, we found is if we take, let's say, Jn, a Jp, let's say, Take JP. JP has drift QP mu PE and has a diffusion component Q dP del P by del X. And as I said, you can go ahead and calculate this QP mu PE. You know the mobility, electric field, we've already done how to calculate electric field. Right at the junction, we know how to calculate electric field, we know how to calculate mu P. And P also, we can calculate, we'll see today's lecture, P also one can calculate. And therefore, one can calculate the first component. But what I said was, if, take it as a sort of a homework problem. If you calculate that, you would find that this quantity is, let's say, 10 to the power 4 or something like that, ampere per centimeter square. This quantity is also 10 to the power, at equilibrium is the same. This is happening at equilibrium. And then when you apply a bias, you'll find that the net current is equal to, say, 1 ampere per centimeter square, the net current. And part of it is being carried by holes, part of it is being carried by electrons. So JP would be even less than 1 ampere per centimeter square. So what we were saying is that JP, the net JP, is a difference of the drift current and the diffusion current. And the two currents are very, very large. And a very small difference between them gives rise to a current flow inside the PN junction. So determining each one of those components, then, in order to calculate current by this approach, you'll have to estimate each one of those current components to a very, very high degree of accuracy, to a third or a fourth decimal place. And that's also very difficult. To compute anything analytically to third or fourth decimal place is very hard. So your location B, so both of these, location A, if you try to sum up currents and determine current, fails. Location B, if you try to do that, it fails. So the issue is, where do we determine? In fact, where do we determine? And this is where I said William Shockley, who first did this calculation, he took up this particular point here at the edge of the depletion region C. He said, we'll compute the current components at C. And so let's see why C may become easier. And then note that I've taken one at the other extreme. A is at one extreme, B is in the middle, C is at the edge of the depletion region. I can also ask you later on, well, do an exercise and see D, somewhere in the middle, not too far and not at the edge of the depletion region. What if you try to compute at D? Is that easy or difficult? Okay, so let's look at what was the argument for C here. Okay, so let me draw the PN junction again. So the argument was the following. So this is the depletion region. Let's call this x equal to 0. Call this x equal to xn, the boundary here. And so his idea was, again, let's put here. So his idea was, let's calculate all the current components here at C, right? So let's write down the current components at C. At C, well, we have J equal to Jp plus Jn, all right? Let's write down Jp. Remember, this is P and this is N. So Jp you will write as Qp mu Pe minus Q dP del P by del X, right? You'll write like this. And then Jn you will write as Qn mu Ne plus Q dN del N by del X, right? So these are the other components. So note that based on how the current flows, you know that you have applied a forward bias V here, and you know that what is happening is holes are getting injected into the N region. Holes are getting injected into the N region. And so we know from our qualitative analysis that what is happening is, if I look at here and if I extend it here, So what is happening is here, if I plot delta P as a function of x. So what is happening is the forward bias creates an excess hole density. You inject holes, and this excess hole density then sort of diffuses and recombines and all that, and eventually if it's very thick, falls to zero. This is what is happening, right? So that's qualitatively we know. At this stage we don't know exactly how it is falling and all that, but this is what is happening here, right? There's an excess hole density at the edge, and then it decreases and falls here. We also know that the bottleneck to current flow is the depletion region. That's where the barrier is. So we know that this region that you see here is not exactly, but it's like quasi-neutral. Quasi-neutral. Whatever voltage I've applied, very little of it will appear across the neutral region here. So we call this the neutral region, but note that I'm not calling it exactly neutral, it's like quasi-neutral. There is some field, something happening here, but very small. Electric field may be there, and you'll see, we have seen earlier why there has to be an electric field, but for a moment, so electric field is there, but it is very small. It's very small, okay? Electric field is there, but it's very small. The other thing is, note that this region is the number of electrons in N region. If you start looking at N region, the number of electrons in equilibrium, if I take a point like this, say, suppose I take a point right at C, okay? At C, right at C, in equilibrium, how many electrons are there? I mean, just outside the depletion region. N equal to? N equal to Nd. And number of holes is? Ni square over Nd, right? So we are talking about Nd, let's say 10 to the power 16 or something like that, say 5 times 16, or let me take 70, just to make it easier, 17, and we are talking about 10 to the power 3, right? 10 power 17 and 10 power 3. Now you apply a voltage. When you apply a voltage, of course, P goes from P to something like P dash, right? You increase. And how much you increase, we don't know at this particular stage here exactly, but what happens is you may increase it to 10 to the power 12. As an example, from 10 to the power 3 to 10 to the power 12, you may increase it because you are lowering the barrier, you're injecting more holes. As an example, you may increase it to 10 to the power 12. Now we are saying region C is like quasi-neutral. So what happens to electrons? Number of holes has increased from 10 to the power 3 to 10 power 12, right? So excess hole density is how much? Delta P is 10 to the power 12, right? Because the background is very small. What do you think has happened to N? N is 10 to the power 17 plus, because it's neutral, it's quasi-neutral. The moment you inject a hole into this particular region, there are a lot of electrons come in and they neutralize it. You cannot, in an N region, you cannot have an isolated positive charge because the electrons would rush in and neutralize it. Just like inside a metal, you can't have a charge because electrons rush in and, the electrons, if you create a positive charge, the electrons rush in to neutralize. Or if you create an excess electron inside a metal, it just disperses away to the boundary. So similarly here, so what will happen is N dash equal to 10 power 17 plus 10 to the power 12, right? N dash also increases to neutralize it because the region is neutral. So if you look at it, if I start thinking about now the following. So if this is the situation, as an example, 10 to the power 12 here, and this is here. You look at this component and you look at this component. Right? We are talking about calculation of current around C. You compare the hole drift current and the electron drift current. What do you see? Start comparing the two terms. Electric field is the same for both of them. Mobility of holes is comparable to mobility of electrons. If I have 400, 500 in one case, I have 1000 in another case, okay. It's not that one is much larger. So, I mean, they're sort of comparable. I don't need to do that. But if I look at P and N, what do I find? N is much, much larger than P. So now you may say it may not always be the same. What if this P dash is 10 to the power 16? If P dash is 10 power 16, is P and N still is N still much, much larger? Maybe yes. 10 to the power 17 is still much, much larger. But what if if you have injected something like 5 times 10 to the power 16? Then what would happen? Then N and P are comparable. But that's where the assumption comes in, assumption of low level injection. Suppose you confine yourself to a case of low level injection. Low level injection means what? The injected carrier density P dash, delta P, is much, much smaller than ND. Then you have low level injection. The amount of excess holes that you have injected are much smaller than the background electron concentration. So you have low level injection. And later on you'll see that most of the time your diode is operating you want to be in the low level injection approximation here. So if that is true, if delta P is much, much smaller than ND, then what can you conclude? What assumption can you make? Compare the two terms, the drift, hole drift and electron drift. What can you conclude from here? Is the sum of all the currents, right? So what can you conclude? Dominated. So what you would say is, I could neglect this, right? See, nobody's saying it's zero. Never say zero. I can neglect it in comparison to one other term which is there. So we can neglect it. We can neglect this. Q mu PE. Neglect it because I have another term here, plus. Both are positive. Note that electric field, if you look at this thing, it's not that one is negative, one is positive. Both are of the same sign here. So what we are saying is, whole diffusion current we can neglect it. Whole drift current we can neglect it. We don't need to consider it. Because there is an electron drift current, and the electron drift current would be hundreds or thousands of times larger. So we don't need to look at this thing here. So what it says is that, what this is pointing out is the moment you say low level injection, delta P, what it is implying is, see, minority carrier current, because whole current in N type, minority carrier current is diffusive. Correct? Minority carrier current. It is the whole current in N-type semiconductor we are talking about. That is diffusive. Only we need to look at this component only. Drift component we can neglect it. We don't need to bother about it. I cannot now. We will focus on the electron current in a moment. So it's diffusive. Okay. So I can then ignore it. Well, we are not going to look at this. Right? We'll consider only this term. Minus Q dP plus here. Right? So we are saying current is equal to minus Q dP del P by del X plus Qn mu Ne plus Q dN del N by del X. Now you may be saying, well, at C you are outside the depletion region. Electric field must be very small. Can I also neglect the drift current? Can I also neglect the drift current? So let's look at that. Okay. So keep this in mind. Let me erase this. Keep this here. So note that N dash. So you have P dash. So are you all seeing the following? Let's say whatever P dash I have in this region, P dash as a function of X. Are you all seeing that N dash will be equal to ND plus P dash X? Sort of quasi-neutral. Are you all seeing this? If I have excess hole density, we are all talking about N region, because whatever happens in N region, same thing happens in P region. It's a complementary nature. So if I have excess hole density in N region, which is P dash X, is varying as a function of X. We are talking about region C, we are talking about X greater than or equal to Xn, that particular region here. So if you have P dash X for X greater than or equal to Xn, we are saying N dash is Nd plus P dash X. It's like quasi-neutral. If you increase the number of holes, you also increase the number of electrons, so the region remains neutral. Remember, initially the region is neutral. If you create excess holes, you create excess electrons, it stays neutral. The two are balanced together. Okay? So with that in mind, let me erase all of this here. Okay? Now the question we are asking is, can we neglect the whole electron drift current and all that here? Okay? So now, note that we have said this is how hole density goes. What is the direction of hole diffusion current? Direction of hole diffusion current? Huh? No? Holes are diffusing from left to right. So holes are positive. So this is the direction of hole diffusion current, JP diffusion. Correct? And this is the direction of current also, because this is the way current has to flow, J, right? Positive voltage we have applied. So JP diffusion is in the right direction. All right. If delta Px goes like this, how do you think N dash goes? What is the variation of N dash? Can you plot N dash? If I were to plot here right underneath it, how would N dash go? Huh? N dash is Nd, which is constant. It will go same way. It's also decreasing. And in fact, if you look at this equation, del N by del X is nothing but equal to del P by del X. Because the region we are saying is quasi-neutral. So del N by del X is del P by del X. So Jn diffusion is what? Jn diffusion, if you look at this term, will be equal to, I can take this dn and divide it by dp and write it as dp del n by del x, which is nothing but del p by del x. I can write it like this. Correct? Jn diffusion, this term, I can write it like this. dn by dp into dp del p by del x, because del n x by is equal to del p by del x. I can write it like this. What does this tell us? This tells us that this is equal to minus dn by dp jp diffusion. So it says there is a diffusion current, electron diffusion current. What is the direction of electron diffusion current? Huh? The direction of electron diffusion current is here. Jn diffusion. Further, what do you find? Jn diffusion is dn by dp is? dn by dp is less than 1 or larger than 1? Greater than 1. dn by dp, if you take dp as, let's say, electron mobility roughly as twice as large or 2.5 times as large, this factor may be greater than 2 dn by dp. So it says Jn diffusion is opposite to Jp diffusion and is twice as large. Well, if there were no drift current, then what would have been the direction of current? It would have gone in this direction. But we know that the net current is in this direction. We know the net current is from left to right. But now we are finding Jn diffusion is twice as large as Jp diffusion and is flowing here. But the net current is from left to right. What does it imply? That this current must be very large also, because that also will drive it. Because remember, when you forward bias it, the whole current must be in this direction and the net electron current also must be in this direction. Both will flow in the same direction. But we are finding JN diffusion is going in the other direction. And so if JN has to go in this particular direction, what does it mean? JN drift must be much larger than JN diffusion, right? And in the opposite direction, and then pushes the electrons also, net flow of electrons in that direction. So you're finding very interesting things happening. There's a current component, JN diffusion, which is actually opposite, going in the wrong direction. So now, this is, let's imagine Shockley sitting here, I mean, at 1940s, 47, 48 or 50, around that particular time, and analyzing and looking at what is happening at point C. So at point C, you want to compute all the current components, right? You want to compute the current. So now you see that, okay, so current is Jp plus Jn. So one nice thing is, well, I need not look at the whole drift current. I need to look at only whole diffusion current. But then, so that requires you to determine del P by del X. Okay? Then when you go to electron current, you find, well, electron current is made up of diffusion and drift, but then you find diffusion current is going in opposite direction. And you know that you can compute this also. Suppose you could compute first whole diffusion current by some means. Then you can easily compute QD and del N by del X. It's just a multiplication. But then you find it's going in the opposite direction. And so you realize, well, I must compute this one also. And then you get into a problem. I need to compute this, then I need to know what is E. And I'm making an approximation that the region outside is quasi-neutral. So E is there, but E must be very, very small. And how do I compute this very, very small E? Right? So you are in trouble again. The same trouble you were there at this particular point. Right? At this particular point, at point A, we said there's only electron drift current. But there is an electric field, but that electric field is very small, I cannot compute it. Now, same trouble you are getting in at C. At C also, I need an electron drift current. And the electric field is very small, so you're in trouble. But then, this is where then he goes and looks at, okay, he says, this is happening at C, right? So, he says, let me look at what is happening at D. Let's look at this point D. What do you think is happening at D? So this is happening at C. What is happening at D? Similar things are happening at D. So he says at D, what are the current components you will have? Let me add, electron current at D will be only diffusive. Whole current in D, drift plus diffusive both, I cannot neglect it. So I'm in sort of trouble now. At D also is something similar. So at D I have to consider this. But then this is where he says the following. This is one of the key points here. He said, if I look at, so my trouble is what? My trouble is that I'm having difficulty computing the electron current, right? I'm having difficulty computing the electron current at C because it involves drift current, and drift current has electric field in it. But then he says electron current at C, and he says, what about electron current at D? So electron current at D is what? Diffusion. And electron current at C is drift and diffusion. And he says electron current at C and D are almost the same. Because what is happening to electrons? Electrons are going, at C electrons are there, then they will go into the depletion region and then come out from the other side. And they say as it crosses the depletion region is small, and there may be some recombination with holes, but that's small in nature. So the crucial thing is, he says, electron current at C is the same as electron current at D. The two electron currents are the same. So, in that case, then what can you write current as? I'm again computing current at C. So the current at C will be equal to this one, the whole diffusion current, plus the electron current. But the electron current I can write now as, this is at C. The electron current I can write as plus Q dN del N by del X. Where? At D. At D. So he says now I can compute the current by calculating whole current in N type and electron current in P type. And if I sum up these two currents, they will give me the net current. Now what is the advantage? I don't have to compute electric field. I'm only talking about a diffusion current. I'm only talking about diffusion current. I'm only talking about, so what he's been able to, by this arguments, what one is able to write, let me write it down here again, is that J is equal to JP at Xn plus Jn at Xp. And these are diffusive current, minus Q dP del P by del X plus Q dN del N by del X. Correct? Yes.
That will be purely diffusing, or we are neglecting the drift part?
Well, we've already talked about that the whole drift current is much smaller than electron drift current. We've already justified that we can neglect the whole drift current, minority carrier drift current. So we end up with this. Now note that if you can calculate this, now whatever happens on P side, the same thing happens on N side. It's sort of symmetry. So what are you left with? Conceptually, what are you left with? What do you have to calculate? Del P by del X. That's all. So the whole problem has been reduced to computing what is del P by del X. Because if you can determine del P del X, same way you would be able to determine del N by del X. This is on the XP side. The thing is symmetrical. If you can do on one side, you can do. So remember, at the end, he has been able to show that I can calculate current if I can compute only one quantity, which is del P by del X. Then I'll know del N by del X and everything is fine. We can compute all of that. Remember, so current looks so complicated, drift, diffusion, everything is boiled down to only one variable. Can I compute del P by del X at Xn? That's all. Can I compute del P by del X at Xn? Then you'll be able to determine this and you'll be able to determine this and the problem is solved. Okay? Right? Now, let's understand. There are people who say current in PN junction is diffusive. The current in PN junction is a diffusion current. Okay? Let's write it down. Current. Now, our job is to calculate current in PN junction is diffusion current. There are people who make that statement. There are people who will make this statement. All of you must have heard current in PN junction is minority carrier current. Diffusion current, minority carrier current. Would you agree with these statements? So the answer is, what I want you to do is the following. We, as a class, we agree and we disagree. We agree and we disagree, both. So first, we disagree. Why do we disagree? Let's look at diffusion current. We disagree. As a class, we disagree that current in a PN junction is diffusion current. Go back and look at this diagram. At any point, take point number C. At point C, if you look at all the current components, you have whole diffusion component, you have electron diffusion component, and you have electron drift current. Is electron drift current negligible? At C, is electron drift current negligible? The answer is no. We saw electron drift current is has to be much higher than electron diffusion current. And electron diffusion current is actually larger than hole diffusion current. What does it imply? The biggest current component in magnitude is electron drift current. The biggest, in terms of magnitude, the biggest component is electron drift current. So we disagree, right? The current in a PN junction is diffusion current? No. It involves drift and diffusion. But then I want you to agree also that yes, current in a PN junction is diffusion current. In what sense? In what sense? Look at this here. In a sense where? What is effectively driving the current is a diffusion part there. Finally, when you wrote down the expression for current, is made up of hole diffusion current and an electron diffusion current. You are writing, right? You're writing only in terms of this and this. So what effectively determines how much current really flows? So we are saying, yes, drift is the dominant component of current. But who determines the drift component? How much should the drift component be? Who decides the magnitude of the drift component? Think about it. We are saying at this point, the largest current component is electron drift. Who decides this electron drift current? Remember we said this electron current is equal to this, right? Remember what is happening to electrons. Electrons are flowing from here to here, right? In terms of actual direction, electrons are flowing from here. Who decides what is the bottleneck for current flow? You're going from point A to point B and there's a traffic jam somewhere in the middle, right? Who determines the rate at which you go from A to B? The traffic jam, right? This is the bottleneck to current flow. So yes, electron current at C is dominant, but what determines the magnitude of the electron current is the diffusion process of electrons from here to here. That determines the electron current, because electron current at this point here is the same as electron current here. The two electron currents are the same. And what determines the electron current flowing in this region here is the slow diffusion process of electrons in that particular region. So what is effectively determining the current is a diffusion current. Is the diffusion of electrons in p-type, is the diffusion of holes in the n-type. That is what our final expression is also telling us. That's what is determining the current, effective current flowing through the device. And in that sense, what we are saying is, yes, we agree. We agree that, yes, it's a diffusion is a driver. What determines the current is the diffusion current. And in the same sense, when you look at diffusion current, the diffusion current is a minority carrier current. Because if you look at the two components, you look at Jp in X, holes in n-type, and electrons in p-type. So what is really determining the current is minority carrier components. But if you look at any particular location, well, the current is made up of both minority and majority. So you cannot say it's minority carrier current. The current is made up of both minority and majority. But what determines the majority is also minority, right? So effectively then, we are saying is, it is determined by minority carriers. The current is not minority carrier current, but is determined by, the net magnitude is determined by minority carriers, okay? The current is not diffusion current, but is determined by diffusion process. So in that sense, we agree with the statement, but in the other sense, we disagree, okay? So there's a lot of confusion regarding PN junction. People say minority carrier current, diffusion current and all that. This, this understanding of why are we calling it diffusion current? Why are we calling it minority carrier current is important to understand, okay? So now in our derivation, what is left now? What do we have to calculate? Only one quantity. What is del P by del X? Right, at Xn. Now, let me ask you, why did he choose C? Why did Shockley choose C? What if he had not chosen C and chosen D? at D. So he would have said, let's calculate all the current components at D. What would have happened? Let me erase all this, okay? What would have happened at D? Okay, let's draw and see why the location is unique. This is what has happened to education, that people, very quickly, books everywhere we teach, we quickly derive. We don't go into why certain things are done. We don't go in depth as to the reason. So what I'm saying is, for example, this question you will never find in any book, why at C? Right? So I'm asking, why not at D? So you're a device engineer, you're thinking, why not at D? Why don't I calculate at D? So remember, at D, if you have to calculate, what would you do? You would say current is, now if you have followed the arguments, you'll say total current is equal to Jp plus Jn. Again, you will do. At this point, you will say Jp is Q mu Pe minus Q dP del P by del X. Plus again, you'll say Jn is Q n mu n E plus Q dn del n by del X. Right? You'll say the same thing. Then what assumption will you make? What will you say? No, the first thing is, you'll compare these two. You'll say electrons are much larger than holes. So you'll say, well, let's eliminate it. Right? So you say, okay, the whole current is diffusive. I have to determine del P by del X. All right, fine. Then you have to determine, this is the electron current, Jn. Now there's a problem in computing Jn, because you have to know electric field. So how do you compute Jn? Well, so you can't compute Jn, but you know that if I go in this region, the Jn in this region would be Q dn del n by del X. So that may be easier to compute. It doesn't involve electric field. So you say, well, I can compute Jn here, but I need Jn at D. So what is the difference between Jn at D and Jn at E? Right, so remember Jn at D and Jn at E. So if you look at Jn at D, Jnd and Jne, obviously note that Jnd and Jne. Remember, electrons are, this is P and N. This is the flow of electrons. So Jnd is obviously greater than Jne. That's the way electrons are flowing. And why would Jnd and Jne be different? Because some electrons which are starting at D and then they reach E, some electrons would recombine. Now I don't know how much they are recombining, right? That's a problem. So now where are they recombining? Well, they will recombine in the depletion region, plus they will recombine in this region, plus they will recombine in this region. How do I minimize my errors? If I don't know how much they are recombining, how do I minimize my error? So I should eliminate this region here. Remember, I should eliminate this region here. So you would say, no, I will not compute at D, I will compute at C. And you should eliminate this also. You will not compute at E, but you will compute here at the boundary. Now you may say, why don't you go inside the boundary? Why not inside the boundary? Well, inside the boundary, you'll see computing del n by del X and all that becomes very hard. Inside the boundary, computation of del n by del X, del P by del X becomes very hard. So there's a unique point. So we have to do a calculation of del n by del X. How do we calculate del n by del X at the boundary? So there is a unique point where you compute the current. At any other point in the PN junction, the computation is hard. Just one place, that's it. Just one place, okay? So everything boils down to then del n by del X in P and same as del P by del X in N. Which is same thing as saying if I know how does Px versus X in N. How does the hole density in n region vary. Because once I know how px varies as a function of n, then obviously I know del p by del x and all that. That is. So this is what the problem boils down to. The problem of current computation is how does px go as a function of x. Now let's further simplify this. Yes. What? Mm-hmm. Why should they be? No, because I don't know, for example, how much are recombining here, right, in this region. So I don't want to compute electron current at D. So the whole thing is I don't want to compute electron current at D, right? At D, I don't want to compute this because to compute it, I have to know E, which I don't know.
But let's say we have a distribution
Huh.
at some time, and then some small amount of electrons come from that side.
Hmm.
Maintain the
No, so they're going from D to E.
Yes.
Electrons are going from D to E. Right.
So at D,
Mhm.
we have some distribution
Mhm.
at T1. At T2.
No, we're talking about steady state.
Yes, yes.
No time part here. Steady state.
No, just to so at time T2 also the distribution has to be constant.
Distribution is same. Huh?
So even if some electrons come meanwhile, they have to go like to B. So why should there be any loss?
Because they're recombining. Number of electrons which enter at, let's say, if you look at electrons entering from this side, right? They enter and then they reach D, and then the amount that reach at C, they recombine here.
But eventually from other side also that electron.
No. The other side is supplying holes.
Effectively, supplying holes is equivalent to electron.
Yeah, but note that we have to determine this current. Go back, yes, the process are electrons, holes, and eventually everything is electrons in the external circuit. But our job is to determine this current, right? So this current, I'm saying I cannot compute at D because I don't know the electric field. This whole component. At D, I don't know the electric field. Because we have to calculate an expression. So I don't know how to calculate an expression for E because E is extremely small. So, but I know, what I'm saying is maybe I can calculate what is the electron current in this region. So we are indirectly trying to compute what is happening to electron current here by looking at what is happening to electron current in P. And what is the difference between electron current in N and electron current in P? How are they two different? They're different in terms of recombination. In terms of recombination. Jn at D at Jn at E are different.
That's what I'm trying to say, that they should be equal.
No, they're not equal. That's what I'm telling you. They're not same. Even in the depletion region, there is recombination and they're not the same. In fact, let's, what we can do is we can draw the currents. Okay, let's look at qualitatively, we can see what is happening here. Okay, so let's draw the currents. Let me draw the p-n junction, a big p-n junction here. And this is our boundary. And let's draw the depletion region. We're talking about forward bias. So we have another boundary here, and let's start sketching. Right, let's start sketching. How does hole density go? This is P, this is N. We are applying a bias here. This is ground here. Hole density, let's plot it. We are under low level injection, okay? So hole density in P region will be equal to about Na. All right, so let's draw it. Na. Almost, if we were to draw, yes, remember the hole density here will be equal to Na plus some excess electron density and all that. But it would almost be like this. Then you reach this region. Then what happens? Hole density. We are plotting Px. Starts to decrease. Comes here. And then starts to decrease and goes like this. Hole density. Well, electron density also you plot. Same thing, electron density. If you take it symmetrical, okay, let's not take symmetrical. So electron density goes like this, constant. Right? This is how electron density goes, Nx. Okay? Now, note that there are both electrons and holes here, in this region here. There is recombination. There are excess electrons, excess holes, there's recombination everywhere. There's recombination everywhere inside my junction here. There's recombination in this region, there's recombination here, there's recombination here, everywhere. Why? Because when do we have recombination? When we have excess electrons or holes. We have excess electrons, holes everywhere. We have excess electrons here, we have excess holes here, and in the depletion region we have both excess electrons, excess holes, both of them. So whenever you have recombination. And please keep in mind that go back to your equation, del P by del T equal to what? Minus del Jp by del X plus Gp minus Rp, right? Okay, we are talking about steady state, correct? Steady state means 0. We are talking about no generation, this, 0. Is there recombination? Yes. Will Jp vary as a function of X? So that was the same argument. Del N by del T, same you can write. They are varying with X. Why are they varying with X? Note that it's because of recombination. If recombination was 0, there would have been no variation in Jp. If recombination were not there, Jp would have been, your argument would have been fine. Jp is the same at that point and that point. Because we have recombination, Jp is changing. Because we have recombination, this thing is changing. So if we were to look at, suppose we were to plot JPX, what do you think will happen with JPX? Start from here. What do you think happens with JPX? Look at PX. PX goes as here, right? What is happening to JPX? It's also decreasing. Because JPX is what? Is diffusion current is equal to minus Q dP del P by del X. It's also decreasing. That's how JPX is going. Okay, let's say total current. Draw a total current. Somewhere, let's say the total current is here, J. How do you think the electron current goes? Net current, remember, this is the total current. This is Jp. How do you think the electron current would go? Will go like this. Right? Opposite will go like that. Because the sum of the two has to be equal to the net current. So the electron current is actually increasing like this here. Note the change in the electron current is actually going like this. How will the electron current here look like? Like this here. So what is the variation of the electron current in the depletion region? In the depletion region, if I go here, the electron current, maybe a little bit, there is a change here. What we are saying is, I'm not drawing it to scale. This region is very, very narrow. So this current and this current is the same. So that's how note that this is how it's flowing. And same way you can draw the this current here. So it goes here and wherever here, like this here. Jp goes like this. The two of them must add up here. So far away, the current is what? Purely electron current and purely drift current. Here, the current is purely electron current because there is no hole diffusion. And here, because there is no P is not varying with X, N is also not varying with X. The current is purely here drift current here at this point. The current is purely drift at this particular point here. Purely whole drift current, electron drift current. And now the currents, you can see here how the currents will change. So this is a variation of electron current, this is a variation of hole current. And we are saying the key thing is if you can determine what is Xn, what is Jp at Xn, and what is Jn at Xp. These are the only two things that you have to determine, and as we said, Jp at Jpx equal to minus Q dp del P by del X. So the whole thing boils down to what is del P by del X, and the whole thing boils down to what is Px in N region. And in fact, this is also easy because we've also, if you look at P in N region, this is Xn, and we are saying it goes like this. So let's say the excess hole density is delta Pxn. So how do we determine this? Well, we go back to our continuity equation. We've already done that. Del P by del T equal to 1 minus 1 over Q del Jp by del X plus Gp minus Rp. So this becomes 0. Jp we write as this thing, so it becomes dp del square P by del X square minus Rp equation. So this becomes dp del square P by del X square, Rp we write as minus delta P by tau P equal to 0. And so we've already done this if you go back. So delta P Xn, delta P X actually goes as delta P Xn e to the power minus x by Lp. We already know this. We have done this in class. Delta P at x, delta P as a function of x goes as delta P Xn e to the power minus x by Lp. So the problem boils down to what is delta P Xn. That's it. What is this value here? If I know delta P Xn, I know delta Px, and therefore I can calculate all this. There's only one single variable I have to determine. What is the excess hole density at the edge of the depletion region? How many excess holes are there? When you forward bias it, how many excess holes are there at Xn? How many excess electrons are there at X? That's it. This is the only problem that is left. After all these arguments, this is the only thing which is left that we have to determine. Delta P at Xn. And how do we determine delta Pxn? All right. All of you know this equation. Say I have EC.
It's the injection only, right?
Yeah, injection only. Just a second. So I have EC and EV. I have non-equilibrium positions. So suppose I were to draw a whole quasi-Fermi level Fn and an electron quasi-Fermi level Fp. Please show that Np equal to Ni square e to the power Fn minus Fp by Kt. Just from definition, what is N? N equal to Ni e to the power Fn minus Ei by Kt. P equal to, just from the definition you show Np equal to Ni square e to the power Fn minus Fp by Kt. Now I will show you, we don't have time, I'll show you in the next lecture that Fn minus Fp is nothing but equal to Qv. This I have to show. In fact, all of you know how to draw the band diagrams. If you draw the band diagram under forward bias, you will begin to see that this is equal to Qv. Fn minus Fp is equal to Qv. So if you assume that Fn and Fp are equal to Qv, right, then we can say, Np equal to Ni square e to the power Qv by Kt. N equal to Ni square e to the power Qv by Kt. Right? Now N, what will you write? N you will write as Nd plus P. Nd plus P here. And P as, you can write it as P equal to this one here. So I'm not doing an exact Ni square here. And N equal to Nd plus P, or N is almost equal to P here. So you get P equal to approximately Ni square, low level injection, e to the power qV by kT. P at Xn. Ni square over Nd e to the power qV by kT. How much is the hole density at Xn? Is Ni square over Nd e to the power qV by kT. If you want to know how much is the excess hole density, delta P, then this will be equal to Ni square over Nd e to the power qV by kT minus 1. So what is the only thing that we have to determine? Only thing we have to show is this one. Yep. Okay, so we need to do the course review, so we'll stop here, and we'll take one more extra lecture in the next week sometime. And so, yeah, Iman, come.